Nope. No.
So when you compare all of those three graphes, you will see that simply changing the scope of the analyzed data can make a significant difference. Another important aspect is the scale of the axis. Here you can see the same graph with a different scaling on the y-axis, leading to a completely different impression. Next up is the context of the data. Now this topic is a huge barrel to open, and there are many scandals regarding false conduction or interpretation of data. But how does it look like in praxis? This is Matt. Imagine Matt is working at a local bank and trying to find out the popularity of online banking in this small town. How would he do that? The simplest method is to make a representative survey and ask people if they use online banking. Now Matt thinks he is smart, and to ease things up he decides to offer the survey online. But what he doesn't think of is that there will be only people answering the survey who have a device with internet connection, which manipulates the result tremendously. The group of people who don't access the internet, like many elders, are completely left out. Last but not least, causation. Causation describes the connection of two variables. For example, the rise of cigarette consumption has a correlation to the amount of deaths by lung cancer. Now, after doing some more research, it can be said that smoking cigarettes can cause lung cancer. But not every correlation between two variables leads to a causation. A perfect example would be the connection of a country's chocolate consumption per capita to its amount of Nobel Prize winners. Here you can clearly see a strong correlation between these two variables, but obviously one cannot state that the cause for a Nobel Prize is a high consumption of chocolate.